Hello. Welcome. All right. Today we are going to be going back to polar. We're going to be doing polar functions again, graphing them and all of that. So today we're just going to remind you how to graph polar functions. We did a lot of changes on this section, and so the note packet that you got was the wrong packet. It's an older version of the notes, and so I've attached in Google Classroom the updated notes for this section. So if you try to take notes in your packet, it's not going to make any sense because you'll have nowhere to write things. But if and the numbers are different, we did different examples and all of that. So make sure you can print it out or just be aware. Yes? Okay, so there are three major types of polar graphs that you will be expected to know how to graph by hand on the AP exam. And those are petal graphs. Those are those ones with the petals, or roses sometimes they're called. Those are also just regular circles, but they look different in polar. Limicons and lemniscates. And the limicons, there were 4 different types. You learned all of these last year. So let's start with petal graphs or roses. So petal graphs are in the form of r equals a times cosine of n theta, right? Or r equals a times sine of n theta. You've got some number in front of theta there. And so it's n times theta. So you can think of, Mrs. Fox always comes up with cutesy ways to remember things. Take times to smell the roses. So cute. All right, so how are you going to graph it? Radius is going to be the length of each of the petals, and that'll be A. If you have a cosine graph, then the first peak or petal will be at theta equals 0, which is your positive x-axis. And then the first peak for sine, it depends on what that n is, right? And so for sine, if it's a sine graph, the very first peak will be at pi over 2 times n, depending on whatever n is there. To remember it, you can think of pi for 2 people. Cute. The number of petals, it depends on if n is odd or even. If n is odd, then there's just n number of petals. But if n is, and you can remember it by odd man out, all by himself is odd man out, it's just n. The number of petals, if n is even, is 2 times n. Even Steven. Steven's got 2 friends. I don't know. But all right, so if the number of petals is odd, there's just that many petals. But if it's an even number, then you'll have twice as many petals as the number that's there. What's really happening is it's always 2n, but with the odd cases, the second set just overlaps the first set. So just so you know, if you were to, all of these, we're giving you shortcuts on how to graph, but really you could plug in angle values and get your r's and then plot them with polar points. Remember, going out r units, going to theta, and then out r units. But I'm giving you shortcuts that you learned last year, and then we'll use them again this year. So, and if you were to plug in points, then you would see that, it ends up overlapping on the second set. All right, so let's do, one more thing. How far apart are they? How far apart? It's 2 pi would be going all the way around the circle, right? And so you're breaking up the petals evenly dispersed around the circle. And so how far are the petals apart? 2 pi over however many petals there are, because you're evenly distributing them around that circle. So let's do an example. Notice that right away, right here, well, even before in the notes, like your notes wouldn't have matched the notes packet you got. So hopefully you printed the new version I put in Google Classroom. All right, so if we've got r equals 6 cosine of 3 theta, the radius is that number in front. It's that a value, so it's just 6. So that's how far out we're going to go for each of the petals. We'll go out 6 units. The number of petals is 3 is an odd number, so we've got 3 petals. The first peak, it's cosine. So cosine says, all right, your first peak is at theta equals 0, which is your positive x-axis. And then each petal is going to be 2 pi over the number of petals. We have 3 petals, so 2 pi over 3 apart will be how far they are. And so your peaks will be at 0, and then you'll add 2 pi over 3, and then add 2 pi over 3. So remember that each of these concentric circles represent the r values. So this first circle here is r equals 1, r equals 2, r equals 3. So that's what each of those circles are on the polar graph. Your angles are here 0, pi over 6, pi over 4, pi over 3, right? So, okay, so you will have a point at the, we call it the pole in polar graphs, but at the origin there, you'll have a point there. And then we've got one peak at 0. So along this x-axis, you'll go out 6 units, 1, 2, 3, 4, 5, 6, and put a dot right there. And then you'll add 2 pi over 3 to 0, which will bring you to 2 pi over 3. So along this line, we'll go out 1, 2, 3, 4, 5, 6, and put a dot. And then if you add 2 pi over 3 to 2 pi over 3, you'd get 4 pi over 3. So your third petal or peak is going to come out along this 4 pi over 3 line. Count out 1, 2, 3, 4, 5, 6. Put a dot there. And then you just want to do your best. I'll draw it so before I show you the Desmos graph, which of course looks beautiful. But just so you know, I don't graph it so beautiful. You're going to just draw a petal coming out, and then a petal coming out, and then funky looking, doot, 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 doot. Plus I'm on this stupid tablet thing, so it really looks funky. But just so you know, I mean, I can do this better by hand than with this stupid tablet, but just wanted to make you feel better before I show you the Desmos graph and show you how beautiful it's supposed to look, right? Mine looks funky too. It's okay. Oh, let me get rid of my ink notations. There. And then there's where it looks, where here's 5, so this is the 6th circle around there. Isn't that pretty? There's a petal graph. Okay, let's do another one. This time sine, yeah. So the maximum radius out is going to be 5, since your A is 5. That's how far out you'll go. How many petals? 2 is right there, and that is an even number. And so you're going to go 2 times 2, so 4 petals. The first peak, we got sine here, yeah? And so you're going to do pi over 2 times 2. It's pi over 2n when it's sine. So your first peak will be at pi over 4. And then how far apart are each of the petals? 2 pi would be going all the way around. We've got 4 petals, and so 2 pi over 4, which of course reduces to pi over 2. All right, so drawing these, you're going to start with the first peak at pi over 4. So you go along pi over 4 right here. We will have a point here at the origin, or the pole. And then along pi over 4, you'll go and count out 5. 1, 2, 3, 4, 5. Put a dot. And then they're pi over 2 apart. Yeah. Or maybe it's better to leave it as 2 pi over 4, because you've got 1 pi over 4 plus 2 pi over 4 will bring you to 3 pi over 4. Count out 5 units. 1, 2, 3, 4, 5. Boop. 3 pi over 4 plus 2 pi over 4 will bring you to 5 pi over 4. Count out 5 units. Boop. And then 5 pi over 4 plus 2 pi over 4 will bring you to 7 pi over 4. Along this guy, count out. Boop. Yeah. And I'm not going to bother showing you again how horrible my petals look. But you'll start there. You'll draw petals going through each of them. And Desmos is beautiful. That's okay if yours isn't. No big deal. All right. So that those are the petal graphs. Now we'll go on to limicons. So limicons are they're in the form of r equals a plus or minus b cosine theta, or r is equal to a plus or minus b sine of theta. Limicons, they're like snails is the nickname for them. I think that's what it means in French, maybe. I have none of you French people to confirm. I believe that's what I've been told. I took French in 8th grade, 1 year of it, so I don't remember everything. Okay, so how do the limicons work? If it's a cosine, then your main orientation, the longest diameter part, is on the x-axis. If it's a plus sign in between the A and the B, then you'll go to the right of the origin. If it's a negative sign in between A and B, you'll go to the left. If it's a sign, your major part of the longest diameter part will be on the y-axis. That's where it's oriented. If it's a plus sign between, you'll be above the origin. The largest part will be above, and then if it's negative, then the largest part will be down. The lengths to place the points. You'll have a larger side and a smaller side. Your larger side, you're just going to add the two numbers together, a plus b, like the absolute value, like ignore any signs, right? Ignore any negative signs or whatever. You're just going to add the straight up numbers to get the larger side. To get the smaller side, you'll just subtract the two numbers. And again, just take the absolute value of it. I'm not adding absolute values in there, but you'll just, if it's 3 minus 5, you'll just do 2, right? You just take the absolute value of whatever. And then the bumps, that's what we're calling the other, like if it's oriented on the x-axis, where do you put things on the y-axis? That's what we call the bumps. If it's oriented on the y-axis, where do you put points on the x-axis? Those are what we call the bumps. And the bumps are always that first number that's in front, the a value. There's a couple different shapes. Well, there's 4 different shapes. First one is cardioid, and that's when A is equal to B. And you can think of a nice, steady heartbeat, right? Your heartbeat, and as long as you don't have arrhythmia or something, you got a nice, steady heartbeat. So when A is equal to B, it makes it looks kind of like a heart with a flattened out butt. Now, second type is a looped limicon. That's when the number in front is smaller than when A is smaller than B. Again, ignoring any signs, you're just looking at straight up the numbers. And you can remember that by if the number is smaller in front. If you remember as a kid, did you ever have someone like flip you over? Like when I was a kid, I would walk up, my uncles would hold my hands and I would walk up their legs and they would loop me, flip me around. Can't do that if a smaller person can't loop over a bigger person, right? So that's how you can remember that. I do have a quick short little clip of a video of Mrs. Fox doing it with little Cassidy, her daughter, back when years ago. She was teeny tiny back then. Hopefully it shows for you. I've found that some of these videos don't always maybe show the video, but hopefully it shows, and if not, hopefully it doesn't completely ruin things, but here we go. All right, so here's Mrs. Fox looping Cassidy. Loop-de-loop, right? Do it again. Cute. All right, so that's the only, Mrs. Fox could do that to Cassidy. Cassidy would not have been able to do that to Mrs. Fox. She wouldn't have been able to do it to me. She wouldn't have been able to, Cassidy wouldn't be able to loop you guys, but you could loop Cassidy. Well, maybe not anymore because now she's in middle school. All right, third type, dented limicon. That's if the number in front is bigger than the second number, A is bigger than B, but it's only slightly larger, like it's not twice as large, right? And so it's a little dented. And so if you have a slightly bigger friend who asks you to sit on the hood of your car, and you look and you're like, should I? And you're like, yeah, it should be fine. They sit on the hood of your car and they dent it, right? Because they were only slightly bigger. So you allowed them to do it. You thought it'd be okay. The convex limicon is when A is also bigger than B, but way larger, meaning twice as big or more. And for that, if you've got an extremely obese person who says, hey, can I sit on the hood of your car? You're going to go, oh, Heck no, I'm not letting you sit on the hood of my car because I know you're going to dent it. Instead, you go, here, I got a nice flat bench for you to sit on. So the dented Limousin will have like a little dent in it. And that's if A is bigger than B, but just a little bit bigger. But if A is bigger than B and a lot bigger, twice as big or more, you would give your friend a seat, a flat bench to sit on. And those convex Limousins have like a flattened out side right there. So that's how you tell the difference on how to graph these shapes. Let's do some examples. 3 plus 4 cosine theta. It's cosine, so it's oriented on the x-axis. Positive in between, this plus sign in between the two values is what's going to tell you it's oriented to the right. The shape, 3, 4. 3 is smaller than 4. That's your little small friend, your little niece or nephew. You can loop-de-loop, yeah, so it'll be a looped Limousin. All right, so how do we get the numbers? We've got, you're going to have a point at the pole or origin. The larger diameter will be on the x-axis and to the right. You'll do 3 plus 4 will give you 7, so you'll count out 7 units to the right and put a dot. When you do 3 minus 4, you'd get a -1. Ignore the negative. You're just doing 4 minus 3, 3 minus 4, whatever. You get a unit of 1, and so you'll go 1 unit. It's a looped one, so you'll go 1 unit to the right because the looped one will be a loop-de-loop and then a round like that. So you go 1 unit to the right there. Your bumps are, so the bumps are where you're going to put points on the y-axis. That's the 3. So out 3, down 3, and then I'll try to show you how I would do this. I always start at the origin here, and you're going to loop through here, go back through the origin. You'll have a bump up that way, and you'll go all the way around and try to cross through there and come back around. Funky! I do a better job with a regular pen, but you get the point, yes? So let me show you it. That's what Desmos looks like. Yay! Okay. Beautiful. Let's do another one. 4 minus 4 sine of theta. All right, sine, so that's oriented on the y-axis. Minus sign in between, so that means your largest section is going to be below, right, or down. Shape, 4 and 4, same number. That is a cardioid because your heart beats at a steady rate. When they're the same number, it's going to look like a cardioid, so it'll look like a heart with a flattened out bottom. So you will also have a point here at the pole, right there. You've got the largest diameter will be 4 plus 4 is 8. You'll go down 8 units, put a dot. And then you see how 4 minus 4 is 0? You can kind of like, it's kind of like the looped, but you don't have a little loop down here. 0, it just means your point's right there. Your bumps come from this first number 4. So you'll go right 4 and left 4, put dots. And then you'll just do a nice cardioid. All right, so we did looped, cardioid. Let's do the convex and dented also. All right, this guy. Oriented, I see cosine and a negative. So it's on the x-axis. The largest part is on the x-axis and to the left of the origin. The shape, I've got a 5 and a 3. 5 is bigger than 3, so it's either dented or convex, right? 5, is it twice as big as 3? No. 6 would be, if this was a 6, then you'd have the flattened out one because 5 is not twice as big, then it's just the dented Limousin. This one doesn't have a point actually on the pole. The convex and the dented ones don't actually go through the origin or pole. Instead, we'll go 5 plus 3 gives you 8, and this is to the left. So 8 units to the left, put a dot. 5 minus 3 would give you 2, so you'll go 2 units to the right, put a dot. Your bumps, so the points on the y-axis will be 5, so 5 and 5. And then you'll just make this a little dented and then curve on through. Here's the picture from Desmos. All right, one more of these. 6 plus 2 sine of theta. This is oriented. Sine says on the y-axis. Plus sign here says above, so the largest part is up above the origin. The shape, 6 is bigger than 2, and it's 3 times as big. So this is the flattened out side. This is the convex limison, where it's a flattened out side on there. All right, so again, this one does not go through the origin. Instead, what you'll do is go 6 plus 2 is 8, sine and positive, so up 8 units, put a dot. 6 minus 2 would give you 4, so go down 4 units, put a dot. 6 is your bumps, so 6 and 6. And it's on the smaller little diameter that is the flattened out side. So I'll show you how I would draw it. I would just kind of draw a little flat line a little bit through there, and then, whoops, missed it. Come on through. Missed it. When I show you on Desmos, it looks more like a circle, but some of them will come out real flat and some of them kind of more round, but it's kind of flattened out like that. So erase these and boop. So I know it doesn't really look like it's flattened out there, but it is. It's a little more flat along that bottom edge than rounded on the top. Okay. Those are your limicons. Let's look at lemniscates. Lemniscates are of this form, r squared. You'll have an r squared, and you will always have a 2 theta here and a number in front there. So you could have cosine or sine. In a figure 8 on a double date, it's always a 2 theta. Cute. And they make figure 8 shapes. That's what the lemniscate looks like. All right, so if it's a cosine, it's always oriented on the x-axis. If it's a sine, it's always oriented on pi over 4, which, by the way, totally matches up with pi over 2 times 2. So it's not a new rule, right? You got a 2 right there, so matches up with the other rule that we learned for the pedal graphs. The maximum distance out is going to be, here's where you got to be careful. It's the square root of a. R squared here, remember that this number, you're going to take the square root of that number to figure out how far out you're going. All right, so let's do an example. R squared equals 25 sine of 2 theta. It's oriented on pi over 4, always pi over 4, because this guy is always going to be a 2. To figure out how far out you go, the maximum distance away from the pole, take the square root of 25 to give you 5 units out. And so this one, you'll put a dot at the pole, the origin. You're going to be going along this line, pi over 4, and you'll go 5 units out. 1, 2, 3, 4, 5, put a dot. And then go 5 units in the opposite direction, 5 units out. And then you'll just do a figure 8. Meow. Yeah, looks like an infinity symbol. Sideways. Twisted. Twisted infinity. All right. That's lemniscates. If it had been a cosine, then you would have just been a straight up infinity that way. Okay, let's do some circles. Yeah, circles are of this form. R equals a cosine theta, or R equals sine a times sine of theta. No number in front of the theta. If there's a number in front there, then they create more than one petal. Think of multiple circles. Kind of works that way. You can think of this is just one petal, so it's just a single circle. It'll be a perfect circle though too. All right, so the orientation, if it's cosine, you're going to be on the x-axis. If a is positive, it'll be to the right of the origin. If it's negative, it'll be to the left. Sine, you'll be on the y-axis. Positive, you'll be above, and negative, you'll be below. Your diameter is a, so that's not your radius, it's the diameter. It'll be the length of the entire circle, that whole diameter there. So There we go. So diameter is going to be just that value A. Let's do two examples real quick. R equals -5 cosine of theta. This guy is going to be on the x-axis and to the left of the origin, and the diameter will be 5. So you'll put a point on the pole or the origin, and then you'll go 5 units out to the left. 1, 2, 3, 4, 5. Put a dot, and then you just do your best to, make it a perfect looking circle. You could plug, if you want to plug in points and figure out how far out, what would be friendly. Cosine, so at 2 pi over 3, your cosine would be 1/2, well, -1/2. So you'd be out 2.5 units. So 1, 2, so you're a dot right there. Maybe that helps you kind of do, I don't know. It doesn't matter. Just try to do your best. There's your circle. All right, one more. 8 sine of theta. So this guy is going to be oriented on the y-axis since it's sine. Above, since it's a +8. Point at the pole, count out 8 units, and then do your best to, I don't know what I just did. Whoopsies. Okay. And then do your best to, whoops, make a nice circle. There's Desmos version. Desmos is always pretty. Pretty, pretty. Okay, there you go. Your homework is a polar graphing worksheet. I have attached that to the Google Classroom, so that way you can do that, print it out, or if you don't have a printer, just do your best on, you can do these by hand. The polar graphs definitely help, right? Having those little circles, but you can still graph them by hand anyway. What does it say? When you see polar functions for the first time in pre-calc, when you see polar functions again in calc, when you see polar functions, let me be cute. All righty. Out of there. All right, I hope you all are doing well. I hope this is working for you. And yeah, come see me in office hours if you have questions, yeah? All right, I hope you have a good one. Have a good day.